It's very important to get good models. All right, so that's the first problem that comes up. How do you get good models? Okay, develop simple forecasting models, and we have this SEMSTA approach, structural economic modeling time series analysis approach that I'll explain to you. We experiment with Bayesian shrinkage techniques and then get a model that works in practice, and then we go back to get the economic theory to explain why the model works. Sometimes you start with the theory and go to the data. Many times you don't know the model, so you start with the data, build empirical forecasting models, and then get the theory to explain why the model works. Okay, so a little talk about forecasting annual growth rates for 18 countries, forecasting turning points, summary, and conclusion. We started this work in about 1985. Our first paper was 87. And this fellow, Garcia Ferrer, came to visit Chicago from Spain. And we played tennis a good part of the summer, but I told him we have to work a little bit too. So we produced this paper. There's another student from Korea, a graduate student from economics, and another student from India, Galati, got in on this work, and Hong and Min, another Korean student, Min. Many of these references are at the end of the first paper in your packet. Okay, or you can go to my collected papers and find a lot of these. So you can see we use this as an excuse to develop new Bayesian methods and try them out in practice. You can see the high field. And another thing you can do is check the Bangalore ISI meeting volume, 1988. We had a beautiful meeting here in Bangalore, and a volume came out of that meeting. Prem Goel and Iyengar were co-editors of the volume. I have a paper in that volume, and Highfield has a paper in that volume, and we use the Indian data to test our model. I think I told you about this. 1978, we had a very bad forecast. That was the year the monsoon didn't come, according to somebody in the audience. So I've been challenging friends in India to pick up on that model and improve it. Apply it to India. The data are there, and see if it works better. If you can get a model that works better. Okay, and then related work, there's a huge literature forecasting turning points in metropolitan employment rates, credibility models with time-varying trend components, the University of Iowa. Two colleagues, Blattberg and George, have a JASA paper, 1991, in the marketing area. And Lee and Dorfman have another way of forecasting turning points. A visitor from Japan forecasted output of metropolitan areas in Japan using these models. So they're very easy to implement, and as a sort of an illustration of the point I made earlier, start simply and complicate if you have to. Okay, now let's look at a nice complicated model that appeared in the literature in Kanui's book, 1957, Analysis of Multiple Time Series Model. H of L is a matrix lag operator. Each element of H is a polynomial in L. ZT is a vector of variables. F of L is a matrix lag operator. ET is a vector of errors, zero mean, and you can make a unit covariance matrix for ET. Now this is called the multivariate ARMA process. Some people call multivariate autoregressive Boole average process. And if F of L is a unit matrix, this is a vector autoregression. Okay, now you can take this model and do algebra on it and solve for the process on an individual variable. So you take the inverse of H of L, that's equal to the joint matrix divided by the determinant, and here's the model. The determinant of H of L is a scalar, so that hits ZIT, an element of Z, and here the ith row of this I wrote like this, and under certain conditions this is well, generally it's a moving average process on the era term, a very high order. Now if this is 7 by 7 matrix, and the polynomials in the matrix are degree 3 or 4 or 2, the determinant has a very large degree. This model predicts the marginal processes will be high order, autoregressive moving average processes, Box-Jenkins models. Empirically, you don't find that. You study, as the speaker mentioned earlier, you don't get huge lags in the processes for stock returns. So this is an implication of this model that says this model is too complicated. And people have tested vector autoregressions in forecasting with priors and without priors. And while they work reasonably well, they haven't been satisfactory. The Federal Reserve Bank of Minneapolis had the Litterman Bayesian vector autoregression model. It missed the 1990-91 downturn. So they scrapped it. Now they're trying to improve the model. So these models they look simple, but they're relatively complicated. Now how can you simplify it? You can break ZT up into two components, YT and XT. And I should mention this feeds in with Prem Goel's talk about how to structure the model for a vector of variables. So you decide YT is a vector of dependent variables. XT is like a vector of input variables. And if XT is stochastically independent of the Y, you get a 0 here, and this is the H of L matrix. These are lag operators. And you get zeros over here and here in F. So just by making the assumption that some of the variables in Z are input variables, like independent variables in regression, you simplify the model considerably. And when you multiply this out, you get 2.3, which is a linear, simultaneous, dynamic structural equation model. And this is much simpler than that. Okay, this is what we call the Semsta approach. The first publication on that was 74, another paper 79, Palm, a student who visited Chicago, a good friend, he's back in Maastricht as a full professor. He published further papers, and this is in the textbooks now, so you can see that representation. Now, I should say you can write this H of L, break it up into H1 of L, H2 of L, and you get a very rich representation. But the question is, what restrictions do you put on the model? So we solve this equation for the individual elements of Y. That H11 has an inverse by assumption. So H11 star, that's the adjoint matrix. There's the determinant. And here's then the predicted equation for YIT, one variable. And you can see it's somewhat simplified. H11, the degree of the polynomial here, is much lower than the determinant of H. H11 is a submatrix of H. So this will be a lower order process. And this is a linear combination of current and lagged input variables. And here's the error term that comes out of this. Now this is called by the engineers a transfer function. Okay? So instead of starting with the big complicated model, we decided we'll start with the transfer functions, determine which of them work in forecasting, and work backwards. From here, each of these equations, work backwards to maybe a system that looks like this. Okay, so we worked the problem backwards. And we started first with an AR3 model, a nice simple benchmark model. People had used this and some of the big models, the econometric models, macroeconometric models, can't beat an equation like this in forecasting. Now here you have a new macroeconometric model in India. Run it against this AR3 model, or random walk model. At Chicago, that came up, and guess who thought of this idea? Milton Friedman. Klein, the Nobel Prize winner, was building these complicated models. Friedman said, can your model beat a random walk model in forecasting? And they couldn't beat the random walk model. Carl Kress did these calculations. Now, if you can't beat a random walk model with a complicated model like this, they built the models in this form. You have a vector of variables. You have a vector of input variables. A tremendous amount of information is in this model. If you can't beat a random walk model, you better go back to the drawing boards and reformulate your model. Okay, so we carry along an AR3. Now here's the first model. What do you think happened with the AR3 when we fitted that? The data for first 9 countries and 18 countries. This model misses the turning points. The economy turns down, this model continues onward. The economy turns up, this model continues to go down. And most of the Box-Jenkins models have that defect. They don't catch the turning points. Now that's very important to predict when an economy will turn down or when it'll turn up. That's the most important part of forecasting an economy, the turning point. Also in the stock market. When will the market turn down? When will it turn up? So we were very worried about this. Finally, I got the idea from Burns and Mitchell's work, put in leading indicator variables. So here is the rate of, this is the rate of change of real stock prices lagged 1 year, lagged 2 years. Here's the rate of change of real money, lagged 1 year. And this variable is the median of these variables over the I countries. So we have 18 countries. This is the median stock return each year. This is like a common effect variable that hits each country. When you put that in, the UIT and the UJT practically become non-correlated, uncorrelated. So instead of having I equal 1 to n, an n by n covariance matrix, all those parameters, when you put this variable in, the covariance matrix, the UI and UJ are uncorrelated. So you have a diagonal covariance matrix. You save a tremendous number of parameters that way. We've checked that out empirically. Okay, so here YIT is XIT beta plus UIT. So you can fit this by least squares and check it out, or you can use Bayesian methods, and I'll show you elaborations of that model. Now, a variation of this model is YIT is the ith country's rate of growth of real GDP. And that's going to be affected by the world conditions. So WT is the median of the YITs for the 18 countries, the median growth rate. So we put that in with a contemporaneous value, WT. And then we have this part that I've explained up here, plus an error term. Now we build an AR3 model for WT. Lagged median stock return variable, median growth rate of money variable, and so on. So we can forecast WT from this variable, this model, put it in here, and forecast YIT. Very simple idea. Now, suppose I want to test the hypotheses about the roots of this process. It's an AR3. What can you do? Well, what we do, we get the posterior distribution of beta 1i, beta 2i, beta 3i, and draw from that. For each draw, we compute the roots, 3 roots. And this has been done. And in many of the draws, 80% of the draws, we get 2 complex roots and 1 real root. And for the draws that lead to the 2 complex roots, the period and amplitude of the process are 1-to-1 functions of the roots. So you can then get the posterior distribution of the period and the amplitude. Turns out the period has a posterior mean of about 4 to 5 years, and the amplitude is less than 1. So that indicates that these models for our data set have damped oscillations of a period of about 4 or 5 years, and the real root has a mean less than 1. So the local trend, but not an explosive trend. Okay, and so here's the equation that I showed you, where these are the growth rate of real GDP, growth rate of real stock prices, growth rate of real money, and there are economic reasons for putting stock prices and real money in the equation. See, news hits the stock market, and the stock market reacts very quickly. The economy reacts with a lag. You have to make the physical adjustments to the news. So the economy reacts with a lag. That's why stock returns lead output. Now, money at Chicago, Milton Friedman, you wake up with a cough in the morning, you check the money supply. Okay? But there's something called the real balance effect in the economic literature. If you get an extra 100,000 rupees, it takes you a little time to figure out what to do with them. You know, what computer you're going to buy or what car you're going to buy. So there's a little lag between you're getting the money and spending it, buying or investing in the market. You have to consult your broker and make up your mind. So there's a lag between the receipt of the money and the expenditure. That's called the real balance effect in consumer behavior. And that's been tested empirically and found to exist. Okay, now here we have the representation of this equation in regression notation. And let's assume the UI is normal, the mean, zero, and covariance matrix, sigma I squared I sub n. You heard all these of the previous days about prior distribution, likelihood function, posterior distribution. So if you put in a diffuse prior and you have a normal likelihood function, you can get out the posterior distribution of the coefficient vectors, the coefficients and the standard deviation. Now, this is for a time series process, and this is exact. No asymptotic approximation, exact. Okay, and you can make inferences about the beta and the sigma from the posterior distribution. You get optimal point estimates, intervals, draw from that distribution, compute the roots, make inferences about the roots, and so forth. Now, the predictive density, here's a vector of next period's input and next period's output. So, as you know, you compute the predictive density by writing down the density of YIF given the parameters, and then you hit that with the posterior distribution. You do this integral, and in the situation we have here with a diffuse prior, the predictive density is well known to be a univariate student T density. And the marginal density of beta I is multivariate student T. Wolfgang's program will compute this for you, or our program will compute this for you. Okay, now I'll just mention this briefly. If you have the set of equations for the 18 countries, you can stack the vectors of output variables. Here are the matrices of input variables, beta 1, beta 2, beta n, u1, u2, un, and you can write this as y equals z beta plus u. And then what we used is a hierarchical model. Beta I equals theta plus delta I, just as Stein did in his shrinkage problem. And then beta is j, a matrix of ones, times theta plus delta, a vector including each of these vectors. So you write down the density of the y's given the z's and the beta, plus this gamma, beta minus j theta, z prime z, beta minus j theta, and here's the density of the random betas. And so instead of this as the likelihood function alone, you've got two quadratic forms. You complete the square on beta, this gamma is the ratio of the variances, and you come up with this as the conditional posterior mean. So it's a matrix weighted average of theta and this. And you can then get this as the conditional mean of the beta I given theta and gamma. If you have a diffuse prior on theta, you can get the unconditional mean like this. So it's beta I hat, the least squares estimate, gamma times this theta curl, and theta curl is the least squares estimate if you assumed all the betas the same. So if all the betas were equal and you regress the y's on the x's, you get this theta curl. And this then is a shrinkage estimate for beta. And when you use that in prediction, you get improved forecasts. Now there's another, I won't go through this, another eta shrinkage technique we've used that can also lead to improvement. Okay, the various shrinkage techniques you can use. Now here we have, for example, for various values of that gamma parameter, Here are the 18 countries. We forecast 74 to 84 each year. These are the root mean squared errors for each country. And here's the median root mean squared error. And you can see is gamma over here, no shrinkage, 2.6. With shrinkage, the median goes down to 2.13 when gamma is equal to 5.0. Now we can put a prior on gamma and integrate out gamma. I just wanted to see conditionally on various gammas how the forecasting got improved. And you're over here, you can see the minimums are these B's, and in each country there's improvement by using gamma not equal to 0. So Stein shrinkage applied to the forecasting problem works in practice. Okay, now here's this world income model. YIT is WT plus this. And then we have the expectation of the future value, expectation of the future value W, expectation alpha I, and so forth. And this is the WF, the ZF prime expectation of pi. This is the process for the median of the 18 countries' growth rates, and AR3 and the lag leading indicator variables. Okay, so when we use that model, we, I should mention here, for forecasting the WT, if we use an AR3, we forecast the median growth rates of the 18 countries, 74 to 84. We get a root mean squared error forecast 2.74. With the leading indicator model, we get 1.48. Vast improvement. The mean absolute error, 2.24, 1.24. The leading indicators really help in forecasting the median growth rate. Okay, so I don't show you any other there, but we do get very significant improvements in forecasting precision using shrinkage and using this leading indicator variables. Okay, now how good are the organization of the OECD runs models, and they have big models with a lot of judgment put in. They get the forecast, they adjust the forecast using judgment. Over 68 to 79 for these countries. Here are their root mean squared errors. Our models with the shrinkage, with the WT, 2.15, the median, they're getting 2.12. With one equation or two equations, we're getting root mean squared errors that are competitive with the OECD big models. Terrible. All right, now let me just show you some of the other models we've used, developed and implemented by using Bayesian techniques. You may want to think about these models. The output for the ith country in the teeth period, output growth rate, is linear in the input variables with a constant beta I plus UIT. Now I showed you the results of pooling. Assume beta IT is random equal to theta plus epsilon IT. Okay, this is a pooling assumption. And this works much better than this. This leads to Stein shrinkage. So we can implement that using Bayesian techniques. Now here's another model, time varying parameter model. So now we make beta I sub t. Now the engineers claim that when you make these parameters time varying, the model adjusts to structural breaks automatically. No, I'm not so sure about that. You better test it. But that's what they claim. So you don't need the structural breaks, analysis if you have time varying parameter models, but you better check that. And then we put a vector random walk on beta IT. So this is an engineering state space model. And then when you pool this model, we made these assumptions. YIT is linear and XIT and beta IT. Then the vector beta IT equals theta t, a vector of means that's time varying, plus an error term, error vector, and then the theta sub t follows a random walk. Okay, so this is an elaboration of this one. And this sort of time varying parameter setup with the pooling works better than the unpooled. And we computed posterior odds on this one versus this one. For all these cases, we have the Bayes factors and the posterior odds. So it's not only theoretical, we have some evidence there. Now, the same thing can be done with this world income model. We have YIT like this and WT like this. Two equations now. We can make these parameters time varying. And we kept the pi fixed. And we put a random, we assumed alpha IT, beta IT equals alpha and a vector of parameters plus an error vector. Then the time varying parameter model, these are time varying, and we put a vector random walk model on this vector of time varying parameters. So you implement this through a recursive updating procedure. Okay. And then we have a pooling model for that. So alpha IT, beta IT, here's alpha T, theta sub T plus the vector of errors, and then the means are following a vector random walk. Okay, these can be implemented through Bayesian recursive updating. You put a distribution on the initial state, you derive everything for the first period. Then you update everything, and you derive everything for the second period. You go period by period to implement these models. Okay, do they work in practice? Now here are our 18 countries. And I must say, I'm very proud of this graphical presentation of the data that I cooked up. It goes beyond Bayesian analysis. We need a Bayesian theory of graphics. If you have time on the weekend, why don't you work up a nice Bayesian theory of graphics? But here are the 18 countries, France, Germany, Netherlands, Spain. And this is the distribution of countries by root mean squared error when we forecast 74 to 87. And the median root mean squared error is 1.74, the minimum, the maximum. Here's the frequency distribution. And you can see nicely centered around 1.5 to 1.99. Now, if we don't use the pooling with the same model, here's the distribution of countries by root mean squared error. The median has gone up to 2.37. 1.74, 2.37. I should add that we use the data 54 to 73 to start up the process. We fit the models 53 to 74, 54 to 73, and we forecast 74. We update the estimates. We forecast 75. We update the estimates, and we go to 87. Currently, we're going to 95. So you can see the difference pooling makes, or shrinkage. Now here's another model. Shrinkage, this is a fixed parameter model. With shrinkage, we get this distribution of countries by root mean squared error. 1.86, this is 1.74. You get a little better results using the time varying parameter model. And here, unpooled fixed parameter model. The median is 2.6. An enormous increase, and look at the difference in the distributions.
Nominal growth.
What?
Nominal growth.
No, there's real growth. Real growth rates, right. Everything's real. Real money, real stock prices, real rate of growth, real GDP. These data are taken from, you can get these data pretty easily from the International Financial Statistics database of IMF. If IMF lasts. IMF has this nice financial statistics database that you can get very inexpensively, and you can download the data for over 100 countries. That's where we got the data for India and tried these techniques. Now let's get on to how do you decide which is the appropriate model? Okay, so we're using, and what prompted this was that for the simplest model I showed you, the fixed parameter model, somebody else, a fellow named Otter in the Netherlands, and another person, Mitnick in Germany, we send our data to anyone who requests it. They used our data and used different identification techniques to find out what the model was. And they got models slightly different from ours. So I said, well, let's put down a model and consider all possibilities. So we have 8 input variables. We used yt minus 1, yt minus 2, yt minus 3, yes. This here, Mitnick added another lagged growth rate in money, so we added that. And here's the median stock return. There are 8 variables. If you think about all possible models, there are 2 to the 8th possible models, 256 possible models. So our problem was to compute odds on all pairs of the 256 models and hope that our model would do well in the competition. So we broke up the model like this. This is the most general model when beta 1 and beta 2 are in there. Okay, so you can think of the hypothesis beta 2 equals 0 versus beta 2 not equal to 0. Okay? And then using the article that Professor Ghosh cited that I did with Xiao in one of the Valencia volumes, we used the posterior odds we derived there, and the posterior odds for hypothesis A versus hypothesis B came out to be this simple expression. Okay, and I think I've got some other versions of that, but this, yeah, here's another version of that. So you can write it like this, where these are the R squares in terms of A and B, and this is derived using a generalization of Jeffrey's Cauchy prior for the scalar case. We have a multivariate Cauchy prior for the beta vector. Okay, and we use that to compute these posterior odds. And that's described in the paper I mentioned to you. The other forms of this, you can express this as a monotonic function of the usual F statistic for testing beta 2 equals 0. So the posterior odds approximate. We use the Laplace expansion that Jeffreys also used to approximate the posterior odds in the scalar case. And this is a pretty good approximation. And we get this monotonic in F. Now, what does that mean, that that's monotonic in F? If we consider F random, K is a monotonic function of F. So if you have a critical value for F, you can use this formula to get a critical value for K. So if you want to use the posterior odds in the sampling theory framework, you can replicate what the F tester gets by defining the critical value for K as this function of the critical value for F. Also, if you view the K that way, if F is a uniformly most powerful invariant test statistic, K will be a uniformly most powerful invariant test statistic, because one is a monotonic function of the other. So the posterior odds have beautiful sampling properties in this problem. Monotonic function of the F statistic. If F is optimal in the sampling theory framework, K has the same optimality properties. If you use the 5% critical value for F here, you can get the equivalent critical value for K. One-to-one function and so on. But what's wrong with that F statistic from a sampling theory point of view? This is a time series problem, autoregression. The F is approximate. Okay, it's not exact. So you have to keep that in mind. But this comes exactly into the posterior odds. Okay, now we also carried along the mean squared error criterion, the posterior odds, mean squared error, Mallow CP, the AIC, the BIC, the SBC, the Schwartz criterion, maybe one or two others. And we noticed this fact. All of them are monotonic functions of the sum of squared errors. So if you have the same number of parameters under the two hypotheses, all of these criteria will order the models in exactly the same way. We stumbled onto that empirically. You notice this is monotonic in this. This one is monotonic in the sum of squared errors. This one is monotonic. So for a given P, the number of additional parameters you're adding, these all give you the same ordering. But the posterior odds gives you a much more meaningful ordering. Okay, so let me mention one other very important thing. Our friend Jeffreys, of all things, considered this problem. When you have 256 alternative models, he raised this issue. You may you may choose a model just by chance. That seems good, gives rise to a posterior odds, high posterior odds, just by chance. If you have 256 models, one may work well just by accident. So he calls that a selection effect. And I don't have time to go through his argument to correct the odds for the selection effect. So he has a procedure, a mathematical procedure for correcting the odds to take account of this possibility. With so many models, one might work just by chance, work well just by chance. Now, this is a huge correction in our problem to the prior odds. Instead of 1 to 1, you multiply this 178.5 times the prior odds. Now, I cooked up an alternative correction. This needs a lot more work. How do you protect yourself against getting a model by chance that works well for the particular sample, but it won't work well elsewhere? Okay, that's a nice problem. Now, here we are out of our 256 models. Here are the preferred models, 1 to 7. I'm sorry, 1 to 6. And the AR3 model, for comparison, was terrible. The odds on it versus the most general model, 25 to 1 in favor of the most general model. The random walk model with drift, 16 to 1 on the most general model versus it. Now our model is the one, number 1, 2.8 to 1 versus the most general model. And then these two, I'll mention 3, came in with very high odds. Okay, they just used the variable y3. No lag y1, no lag y2, just y3. So yt is regressed on yt minus 3 plus some other input variables. And then this is Mitnick's model, 2.18. And that did pretty well relative to the general model, but our odds were 2.8 over 2.18. Our model was slightly favored relative to his, but his model did very well. Okay, so this then is the mean squared error within sample, and then we have the data extended 1954 to 87, and here's the out of sample mean squared errors, and here we recomputed the odds using the data 54 to 87. And again, our model 6 to 1 versus the broadest model. And you can see these models with Y3 alone are favored somewhat. Does anybody have an idea? I'm really worried about this. Why would just use of YT minus 3 work? It turns out if you have a negative coefficient for YT minus 3 and you compute the roots of the process, you get 2 complex roots and 1 real root. The 2 complex roots give rise to about a 5-year cycle, and the amplitude is less than 1. So, and then you have a real root with amplitude less than 1. So with 1 coefficient, you get the cycle. You don't need 3 in this problem. It won't work in general. For this problem, using just YT minus 3, 1 parameter rather than 3. And as you know, these model selection procedures have penalties for adding extra parameters. So that's, I think, why these models are working well. 15 to 1 versus the broadest model. But all of this is very, very operational. And then we get unpooled autoregressive leading indicator, autoregressive world income model. Posterior odds for fixed versus time-varying parameter models. Okay, so fixed versus time-varying parameter models. And here's the posterior odds on the fixed. So for Australia, 6 to 1 favoring the time-varying parameter model. Okay, and for the autoregressive leading indicator world income model for Australia, 3 to 1 favoring the time-varying model. And then when you add the pooling, you can do this with pooling, the odds we computed for all these variants for all the countries. Okay, now what can you do with the odds in addition to model selection? Just measuring the odds and so forth. Well, if you have a fixed parameter model, a time-varying parameter model, fixed parameter model, time variant parameter model. This is the state of the world. It's either this or this versus your choice, this versus this. You have a loss structure. Now here are the posterior probabilities on this model, on this one. You can compute expected loss. If I take this action, P1 times 0, P2 times C1, gives you that. If I choose this model, my expected loss is P1 times C2. And then you choose the model with the lower expected loss. That's one way to choose between the models using expected loss. Now here we didn't bring in the benchmark model. You can bring in the benchmark model and get the probability of a fixed parameter model, time varying parameter model, benchmark model. So you can allow yourself to choose the benchmark model. As I asked the question a little while ago, if these are both terrible models, you may want to use the benchmark model. So you can compute expected loss under the 3x3 loss structure and choose the model with the lowest expected loss. And this also relates to the posterior odds. If C2 over C1 is equal to 1, symmetric, you choose the model with the posterior odds larger than 1. Okay, now the other thing you can do, I haven't included that here, suppose you want to combine this model and this model. You can look for the combining density that's closest in terms of a Jeffreys-Kullback-Leibler distance measure. So you have the probability on the distance of this model from the combining model, plus the probability of this model's distance from the combining model, and then you can find the combining model, the linear combination of the two models that provides minimal distance, subject to its being proper. And under certain conditions, you just get a linear combination of the two models weighted by P1 and P2. So this is another possibility that's been overlooked in this literature, but the forecasting people work with they combine models and combine forecasts very, very often. So here you can do that from a Bayesian point of view if you use a Jeffreys-Kullback-Leibler distance measure and find the density that's closest to these individual densities, and that gives you a nice model combining technique. Now, I mentioned earlier we also forecast turning points. With this model or any model, we can get the predictive density for YF. You have to define what a turning point is. So if you have two growth rates below the third, and the fourth, next year's growth rate is below this year's growth rate, that's a downturn by definition. If you have two growth rates below the current growth rate, and next year's growth rate is not below this one, that's no downturn. So which do you pick, downturn or no downturn? That's the problem. Now we have a predictive density for P of yt plus 1. You write down the density of yit plus 1, given the parameters in the past data, hit it with a posterior distribution, integrate out the parameters, and then you get the predictive density. And then if you integrate that from minus infinity up to the current growth rate, that gives you the probability that yit plus 1 is less than yit. And that's the probability of a downturn. Okay, so that is this chart I think I showed you earlier. Here's the predictive density. Here's the current growth rate. This is the probability next year's growth rate will be below this year's growth rate. So if the Prime Minister asks you, as an advisor, what's the probability of a downturn next year? You give him this number, PDT. That's the probability. Next year's growth rate will be below this year's growth rate. But if you want to make a forecast, downturn or no downturn, you can use this 2x2 loss structure. Here are the forecasts, downturn or no downturn. Here are the outcomes. Here are the probabilities. So you just compute expected loss. If you take this action, this times 0 plus C1 times this, that's your expected loss. If it's no downturn, you take that action, C2 times PDT, 1 minus this, that's it. And you choose the forecast with the lower expected loss. Okay, now we've applied this to the data for 18 countries, initially 158 turning points, and we got about both upturns and downturns, no downturn and downturn, upturn, no upturn. 158 turning points, we got about 70% correct, whichever model we used, 70%. I'll show you the chart. Here, I'm going to show you the chart. So this was 1974 to 86, 158 turning points. Here are the different models, and here's 70%. So whether we use pooled models or unpooled models, time-varying parameter models, fixed parameter models, exponentially weighted, autoregressive techniques, we get about over 70% correct. And that's both downturns and upturns. If you consider just downturn, no downturn forecast, 76. Here's the percentage correct. So 70% is about here. We're doing much better on the downturn, no downturn forecast than the upturn, no upturn forecast. Here we're getting about 70%. But you see up here we're getting about 85% correct. Okay, so I sent Milton Friedman the paper based on this. He looked at it. He said, why don't you extend the sample from 86, you see? Why don't you go to 95 or 98 or something? He thought we had looked at the data. That's why we're getting 70% correct. So we extended the sample and we got about 212 turning points. And fortunately, the results held up. Still 70% roughly correct. So we published a note recently, an answer to a question raised by Milton Friedman that's quoted in the references to the first article. And he was flabbergasted. He says, Arnold, it's black magic. And I said, we were lucky. So this is very, very interesting. Now, for each country, for each episode, now here is Belgium. In 1974, 2 growth rates below the third. Now for 1974, the probability of a downturn is 0.82. And this asterisk means we predicted downturn. So here in 1977, the probability of a downturn 0.9, and the economy turned down. So you can get these probabilities year by year, and they're very informative. I mentioned earlier, Charles Whiteman has gotten the governor of the state of Iowa, so he can understand things like this. What's the probability tax revenues will turn down next year? Whiteman tells them it's 0.9. Oh, your degree of confidence in the proposition is 0.9, the governor says. He understands probability theory. So this is very important. And here you have upturns and no upturns by country. I won't take you through the details of that, but that's it. Now we cooked up some benchmark models. How am I doing on time? Benchmark models. Eternal optimist, when he's at the top, he always predicts no downturn. At the bottom, he always predicts upturn. Eternal optimist. The eternal pessimist, at the top, he always says downturn. At the bottom, he says no upturn. The deterministic four-year cycle person, at the top, he says downturn. At the bottom, he says upturn. Okay, here are the number of incorrect forecasts by the eternal optimist. 93 incorrect forecasts, and percentage of incorrect forecasts, 59%, 41%, 32%. Our model gives about 18% incorrect, 20% incorrect. So we're beating the eternal optimist, the eternal pessimist, and the deterministic four-year person. Now somebody posed a problem, suppose you flip the coin. Heads, downturn. Tails, no downturn. At the bottom, flip the coin. Heads, upturn. Tails, no upturn. Well, if you do that, and you have 158 turning points, you expect 1/2 times 150, 256. So you expect 178 turning points. Well, you don't get anywhere near that. The actual number is 107. And when we add up the probabilities, this model predicts 104 turning points, 101, 101. These models, 98. But the coin flipper